Hello and welcome back. In the previous video, we observed something quite surprising. A peak current mode controlled buck converter was still regulating the output voltage correctly. The crossover frequency remained unchanged, the phase margin was still large. Yet the inductor current suddenly started oscillating from one switching cycle to the next. So where do these oscillations actually come from? And why do they appear once the duty cycle exceeds approximately 50%? In this video, we will answer those questions. We will look inside the peak current mode modulator, understand how small perturbations propagate from one switching cycle to the next, and develop a simple discrete time model that explains the origin of subharmonic oscillations. Once we understand this mechanism, the famous 50% duty cycle limit becomes almost obvious. So let's begin. Before we investigate why these oscillations occur, let's first recall the behavior we want to explain. Here we can observe the internal switching waveforms of a peak current mode controlled buck converter. At the top we have the control signal together with the measured current signal. In the middle we have the PWM signal generated by the current comparator. And at the bottom we have the inductor current. Notice that the switching pattern is no longer repetitive. The PWM pulse width changes from one switching cycle to the next, even though the operating point remains essentially unchanged. As a direct consequence, the inductor current also alternates from cycle to cycle instead of repeating the same triangular waveform every switching period. This is the characteristic behavior known as subharmonic oscillation. The important question is no longer what is happening. We can clearly observe the oscillations. The real question is, why does the peak current mode modulator naturally produces this behavior? To understand where these oscillations come from, let's take a closer look at what happens during a single switching cycle. The black waveform represents the steady-state inductor current. Under steady-state conditions, every switching cycle is identical. The current starts from the same value, rises with slope m1, reaches the commanded peak current reference, and then falls with slope m2. Now, suppose a small disturbance appears. This time we will assume that both the initial inductor current and the commanded peak current contains small perturbations. The blue waveform represents this perturbed switching cycle. Because the current starts from a different value and the comparator threshold has also shifted, the intersection between the inductor current and the reference no longer occurs at the same time instant. As a result, the PWM comparator changes the switching instant, producing a different duty cycle for that switching period. That modified duty cycle changes the current at the beginning of the next switching cycle. In other words, disturbances are transferred from one switching cycle to the next through the modulation process itself. Every switching decision slightly changes the initial condition of the following switching cycle. This is the key idea. Peak current mode control is not only a continuous time system, it is also a sampled system, where the PWM comparator makes one switching decision every switching period. To describe this cycle-to-cycle behavior mathematically, we can use the discrete time model shown below. A complete derivation of this model is included in my full peak current mode control course. For this video, we will focus on understanding what the model tells us physically. Notice that everything ultimately depends on a single parameter alpha, which depends only on the duty cycle. So let's see what happens for two different operating points. To better understand the intrinsic behavior of the modulator, let's assume that the current reference remains constant. That means we can ignore perturbations coming from the reference and focus only on how an inductor current perturbation evolves from one switching cycle to the next. Now consider a duty cycle of 68%. Using the expression for alpha, we obtain alpha equal to minus 2.125. That number alone already tells us everything. Notice two things. First, alpha is negative. That means the perturbation changes sign every switching cycle. The current alternates from one side of the steady-state waveform to the other. But the second observation is even more important. The magnitude of alpha is larger than 1, which means every new perturbation becomes larger than the previous one. If we start with a small perturbation, after one switching cycle it becomes minus 2.125 times larger. After another switching cycle it grows again, and after the next one it becomes even larger. Instead of disappearing, the disturbance is amplified. This is exactly the mechanism behind subharmonic oscillations. The converter keeps making switching decisions, but each new decision actually increases the error from the previous switching cycle. Now let's look at the opposite operating point. Suppose the duty cycle is 40%. Using the same expression, we obtain alpha equal to minus 0.667. Again, alpha is negative, so the perturbation still changes sign every switching cycle. But now there is one crucial difference. The magnitude of alpha is smaller than 1. Instead of growing, each new perturbation becomes smaller. Starting from the same initial disturbance, the next perturbation is reduced, then reduced again, and again, until it eventually disappears. So the converter naturally returns to its steady state operating point. Every switching cycle naturally corrects the error from the previous one. The perturbation is still sampled every switching cycle, but now the sampled dynamics attenuate the disturbance instead of amplifying it. And that is the fundamental difference between operating below and above 50% duty cycle. We can now put everything together. From the previous examples, we saw that the behavior of the perturbation is completely determined by the coefficient alpha. If the magnitude of alpha is greater than 1, the perturbation grows from one switching cycle to the next. If the magnitude of alpha is smaller than 1, the perturbation gradually disappears. So for stable operation, we simply require following condition. Now let's substitute the expression we obtained earlier for alpha. Solving this inequality gives a remarkably simple result. And this is one of the most important results in peak current mode control. It tells us that the natural dynamics of the peak current mode modulator are inherently stable only when the steady state duty cycle is below 50%. Below 50%, perturbations decay naturally. Above 50%, they grow from one switching cycle to the next, producing the subharmonic oscillations we observed earlier. Before we finish, let's summarize the key ideas from this video. First, peak current mode control is fundamentally a sampled system. The PWM comparator makes one switching decision every switching period, so disturbances naturally propagate from one cycle to the next. Second, the evolution of these perturbations is completely described by a single parameter alpha. If the magnitude of alpha is smaller than 1, perturbations gradually decay and the converter returns to its steady state operating point. If the magnitude of alpha is greater than 1, perturbations grow from one switching cycle to the next, eventually producing subharmonic oscillations. And finally, this leads to the well-known stability condition. The steady-state duty cycle must remain below 50%. Understanding these concepts is essential because they explain why subharmonic oscillations appear even when the voltage loop itself is properly designed and appears stable. At first glance, this seems like a major limitation. After all, many practical converters operate above a 50% duty cycle. Some boost converters operate there continuously, and even buck converters can exceed 50% during startup or large load transients. So, how do real converters avoid subharmonic oscillations? The answer is surprisingly elegant. Instead of changing the controller, we change the modulation itself. By adding a small artificial ramp known as slope compensation, we intentionally modify the sample dynamics of the system and prevent perturbations from growing from one switching cycle to the next. We will explore how slope compensation works in an upcoming video. If you would like to explore these concepts yourself, I have made several free peak current mode control resources available on HK Academy. These include LT-SPICE simulation models, control-oriented converter examples, and GNU Octave scripts that you can use to experiment with the sample dynamics of peak current mode control. Try changing the duty cycle, modifying the converter parameters, or observing how small perturbations evolve under different operating conditions. Seeing the behavior directly in simulation is often one of the fastest ways to build intuition for switching converters. If you would like to go even deeper, I'm also developing a comprehensive course on digital peak current mode control for buck converters. The course covers the complete engineering workflow, including peak current mode fundamentals, small signal modeling, type 2 compensator design, subharmonic oscillations, slope compensation, digital implementation, and complete verification using simulation and real hardware. You can download the free resources and follow future course updates on HK Academy. Thank you for watching, and I will see you in the next video.